Hey, look at that, we're recording. So I don't know what just happened in terms of the settings on Zoom, but here we are. So Monica Shoemaker, The Power of Art, a Mental Health Therapy. You have the floor.
Thank you. I wanted to make sure if you want my video off, I will turn off my video. I think I missed that part of the instruction.
I think it's fine for you to leave it on. Thank you so much, Monica.
Okay, great. So hello, my name is Monica Shoemaker. I am a senior in the Bachelor of Applied Science and Behavioral Healthcare program and conducted this study in the spring of 2019 with the advisory help of Dr. Sharon Raz and Dr. Rex Rempel. I will be graduating in 2 short weeks and have an interest in serving communities of vulnerable groups of people living with mental health and substance use disorders. I currently intern at Crisis Connections in Seattle, taking phone calls from individuals in many states of crisis, including suicide. It is the combination of a deep interest in art and personal experience with mental illness and addiction that led to my involvement in conducting this research study. I would like to add that I'm grateful for the involvement of multiple members of the administration, school staff, and students that were involved in the interview and research process. This project and poster were also presented at the University of Washington 2019 Research Symposium, which as of last year became the largest research symposium in the country for 4-year colleges. It was an honor to represent LWTech at this event. Now I will begin my presentation with my research hypothesis and introduction. My project is titled The Power of Art, a Mental Health Therapy. To understand the effects that the Healing Art Club has on its participants, I am conducting in-depth interviews with key students and staff. I hypothesize that participation in the Healing Art Club helps students express themselves in a therapeutic way, fosters feelings of belonging to the community, and contributes to their overall health. The data collected is a helpful start in encouraging college communities to adopt similar programs and to promote positive mental health on campus. What is art therapy? Art therapy is an application of visual arts in a therapeutic context. It supports self-discovery, self-esteem, and emotional release. The Healthy Minds study conducted at LWTech found that 53% of people would think less of someone who has received mental health treatment. The creation of the Lions Pride Healing Art Club was intended to help students develop healthy coping skills that are familiar with mental illness and/or addiction. The goal of this study is to better understand the benefits of participation in creating art to aid participants' mental health condition. Baylor University is just one example of another school that has conducted similar studies and practices. Participation in such clubs has been positively regarded by students and campus communities. Creating safe spaces for people in need is an important extension of the support that can be found on campus. My research design is made up of qualitative research based on 12 in-depth interviews with students, staff, faculty, and administration. These interviews provide information pertaining to participants' experiences and viewpoints on the Students' Healing Art Club. And lastly, content analysis is used to analyze interviews, cluster and categorize their data, and highlight main themes. I will now highlight a few of my findings. First, students struggle with mental illness and substance use disorders and are looking for some sense of community in a non-judgmental way. One faculty member states, "I see a fair amount of students struggling with either current or previous addiction that are looking for a sense of community on campus." In regards to mental health and substance use disorder management, one study participant stated that the club could lead some people to find or identify the risks and appropriate supports. Second, students feel that participating in the club helps them connect with others and be an active part of the community. One example of this comes from a student government leader who recognized that students who participate in the club feel that being part of it helps them connect with others on campus. Through consistent observation and years of experience on campus, one interview participant conveyed that it's a moral imperative for us to offer a healthy, safe alternative to keep students from moving into old patterns. The last finding I want to share is that participants feel that art-related activities contribute to their overall health. One interview response: being involved in an artistic activity contributes to overall health. Students draw parallels between physical and mental health and want more mental health support on campus. And one student leader states that students come to us with issues that impact their ability to be healthy. We have limited services to provide. Tying all of my data together, I have found that students find that participation in the art club is beneficial to their own mental health and overall health. Students feel that the club can be a safe space where expression of feelings and struggles are welcome without judgment. The Healthy Mind study shows that most students struggle with mental health-related social stigmas. Students also express their feelings of connection to the college community through the participation of the Healing Art Club. And overall, participating in the art club is regarded very positively by students and the campus community. I want to quickly share some information about the photos on the poster and the wooden and ceramic coasters. These were a project that I organized and put together as a part of the activities for the school's Mental Health Awareness Week last year. These painted coasters were the immediate results from dozens of students that participated. After they dried for a couple of days in the ASG office, I took them home and clear coated them with UV resistant sealant and brought them back to the school to be picked up by each student that participated. I had wanted to do another event like this for Mental Health Awareness Week this year, but sadly COVID happened and all in-person activities were put on hold. I want to end with a quote from a student that participated in the art club activity and research. Making art with the Lions Pride Art Club gave me a wonderful break, where my stress and anxiety took a backseat to creativity and art. Thank you so much.
Wonderful. Thank you so much, Monica. So Monica, feel free to go ahead and stay on. And I do invite any audience members, that includes other students, that includes faculty, administration, that also includes any non-LWTech audience members. Please, if you have any questions for Monica or any of our presenters, feel free to go ahead and put those into the chat window, and our monitors will take a look at those questions. If we don't have any questions for our presenters, then we can go ahead and move on to our break, but we'll leave it to the moderators at this point. And I do have at least one person saying that they are currently typing.
We have one question. This is for Monica. What did you learn in doing this project?
So I learned that there were more students than I had originally anticipated that I spoke to, that all agreed that there was a lack of support and a lack of resources on campus for people struggling with mental health and addiction issues. I especially wanted to ask not just about mental health, but also substance use disorders, because I know that that's a huge, it's a huge epidemic, and it's really difficult for a lot of students to find the right type of help. It's one thing to have information on mental health, but it's another to be able to point people in the direction for assistance with substance use disorders. And a lot of people, I think, are more hesitant to talk about that subject than they would be, you know, a mental health disorder, maybe like anxiety, depression, that type of thing. So I wanted to kind of like open up the doors to that. And I found that a lot of students were really open to those ideas and the thought of, you know, kind of expanding upon that on the school campus.
Another question. Can you expand on the process of content analysis? How did you cluster and categorize the data? The
process of the content analysis, after I kind of designed a lot of the questions that I wanted to ask the participants. I really wanted to reach out to key people in the school that had a higher knowledge of maybe what students were currently experiencing or what students had experienced in the past. You know, so I was able to interview the president of the school, and I was able to interview the vice president of student services and different faculty members that really had kind of a hand in that group of being able to help with like mental health issues or substance use disorder. So it was a lot of just reaching out to key people and finding real, honest and raw opinions about a tough subject like this, and being able to then analyze each interview and kind of pick out key points from each one that kind of created had a common theme throughout each one. And then also talking with the students and being able to find out from them that their opinions and views on these things also aligned with that of the faculty members that I interviewed.
Thank you, Monica. I'm going to share one more questions, though there are more because of time restraint. Did you see any other schools or organizations use art therapy?
I did speak to one student from another school that said that they had just recently started a type of club surrounding that. And they had even expressed wanting to become a part of that themselves, to get more involved, and also wanting to look into maybe creating a program, you know, developed around using art therapy as, you know, a mental health therapy or to help those with substance use disorders. So I'm finding that it is reaching out to other schools and becoming more at the forefront of using a creative type of therapy to treat these issues.
Thanks, Monica. I think I can sneak in one more question.
Yeah, I went over a little bit on my time, so so we can go to like 132 or 133 for sure.
Okay, thank you. This question is regarding the variety of art you made. What did you find that the students did better with certain mediums? What were those mediums?
I think that students really had a lot of fun with the art project that I had put together. The art that I tend to, like, I guess, specialize in or kind of turn to when I'm needing some art therapy myself is called acrylic pouring. And so being able to mix and kind of pre-make these colors, the paints, you know, the pouring mediums, and then they kind of had that ease of just putting the colors together that they wanted. In a sense, being able to make a mess was more therapeutic and more fun for them than having a more structured setup, you know, like with, you know, painting or coloring on pictures, which is all very helpful. But I think the process of being able to just make a mess and know that that was okay to do, and just to be unencumbered and just like, you know, they had freedom to just watch these different colors and paints flow. I think was really, really fun for them to be able to do that. And then clearly, you know, them not having the responsibility of cleaning up was really helpful too. They just got to come and make a mess and then enjoy what they created and then walk away. So I think that was a big part of what was fun for them, was being able to, you know, have that space and that freedom to just be messy.
Thank you, Monica. Over to you, Michael.
All right. That was wonderful. Thank you so much, Monica, and thank you for those wonderful questions. And I always love hearing students, you know, backing up their research. It's wonderful. Thank you so much, Monica.
Thank you.
All right, so in about 3.5 minutes or so, we will have Thomas Choice go ahead and talk about scratch fabrication of apparatus for local aluminum recycling. And so let's see. So I'm just going to, oh, good, okay. So we will go ahead and resume again promptly at 1:35. Thank you very much. All right, so just here in a moment, we will go ahead and get started again with the next talk by Thomas Choice. So, hey, we got our first presentation finished from our first annual symposium. And so with that, I realized that this 5-minute break actually can be a little bit awkward. And so what I'd like to invite the audience and presenters is potentially, if we still do have questions that anyone would like to ask, and we are waiting for that time for the next presenter to present, it's absolutely fine for us to continue fielding questions. We originally built in that 5-minute time just in case, you know. So it is 1:35, and so Thomas Choice, you have the floor, sir.
Right, thank you, Professor Rodriguez. Can everyone hear me all right? Kind of? Okay.
Yes, we absolutely can. Thank you.
All right, thank you. So, hello everyone. My name is Thomas Choice. I am a student at Lake Washington Technical College, and I'm studying biology to eventually receive, in hopes of receiving a biology 2-year degree. My project is about the science and technology of aluminum recycling and my journey toward building it from the ground up. This project was developed over the past academic year. So it's been quite a while there. Let's see. So why aluminum, right? Why melt aluminum? What purpose might that be? Well, it's so that my ultimate goal is to study this process so that I may eventually be able to understand how aluminum is created from scratch, and then further improve it. Currently, aluminum is derived from bauxite ore, which is often mined and shipped from continents as far away as Africa and South America, places where local restrictions do not stop the pollution of the surrounding environment with heavy metals and the poor treatment of workers in dangerous mining conditions. I would like to find a way to obtain aluminum from local soils instead, to not require wasteful mining and shipping, and can instead improve the local economy. But for now, I am working on aluminum recycling, local aluminum recycling, so that we may not need to use immense fossil fuels to ship recycling materials to one location, but instead perhaps have many smaller locations near urban centers. For this project, my goals were to learn the aluminum recycling process and convert aluminum scrap into aluminum sheets, similar to ones that are used in industrial processes. My first step, as seen in the methods section, was to learn all the dangers and the necessary processes to melt aluminum. Then the rest of my procedures were created off of that. I would need to obtain wood fuel, create fire-resistant bricks, build a furnace to create charcoal, because charcoal burns at the required temperature to melt aluminum. I would then use that charcoal in a aluminum melting furnace to create ingots, which will then be flattened in a heated rolling mill powered with the charcoal mentioned earlier to create aluminum sheets. And I chose aluminum sheets because they are used with a hydraulic press later to create aircraft, electronics, and almost every product in the modern world. In the results section, on the left-hand side is a row of fire-resistant bricks that I create from local soils. Next to that is the charcoal creating furnace currently running in that image, and next to that is the aluminum melting furnace. On the bottom is an example of some of the charcoal that I've created from locally sourced lumber materials. And on the bottom right-hand corner are 2 ingots, one of which I am holding in my hand for scale. In conclusion, I am at step 9 of my procedures. I will then need to build a rolling mill and flatten the aluminum ingots. Afterward, I will test the aluminum sheet in various applications for strength and reliability. Eventually, I would like to work backwards and research and develop an efficient way to extract aluminum from local soils, convert it into pure aluminum ore, and then create aluminum from scratch that way, so that we do not need to rely on poor labor practices and we do not have to spend immense fossil fuels to obtain this valuable resource. My name is Thomas Choice. Thank you for listening. Am I a little bit early?
No, you're doing fine. I think our moderators are just looking at some of the chats and looking at potential questions that we have for you. Very nice work.
Thank you.
So,
Thanks, Thomas. We have a question for you. How do your current methods compare to the aluminum recycling in the industry? How are they different or improved?
Well, the melting process is fairly similar. It's often they use like fuels like propane, similar to propane instead of charcoal, because it burns at a much hotter temperature. Other than that, everything is almost the same, just immensely scaled up.
Thank you, Thomas. Another question. Where did you get your inspiration for this innovation?
Well, originally, I have always been interested in melting metals. So I had, on a whim, tried melting zinc. I had some spare zinc around and melted it in a small steel cup in a fireplace. And I thought, I didn't have much zinc, so I wanted to melt aluminum because it was readily available and had more applications. But as it turns out, as I have learned, melting aluminum is exponentially harder than melting zinc.
Next question. How long does it take to make charcoal from scratch?
It depends on my current process, right? It takes about a few hours per burn, I would say. On the bottom here in my results section, it showed I have written down that per about hour of burn time, I'm able to create just a little under 1 pound of charcoal. I'm currently developing a better strategy for making charcoal that can make almost more than twice that much per hour, but I'm still kind of smoothing out the process.
Another question, how difficult has it been for you to source aluminum to recycle?
Aluminum is sadly kind of common around here. It's kind of easy to find cans that people have not thrown away on the sidewalk and in the yard. So in the local public areas. So I just collect them, and it prevents a little bit of litter as well.
Thomas, is this something you are learning in your program at LWTech?
No,
Or this
I'm
is
not.
a personal project.
This is a personal project.
What was the most challenging aspect of this project?
The keeping, probably to melt the aluminum itself, actually. The most challenging part is probably having to work backwards multiple times, because I would have originally attempted to melt aluminum with different fuels I had available, and I found out kind of the hard way at first that lumber, no matter what, just doesn't melt aluminum reliably. And then even with charcoal, I need to have a very specific setup and a very specific amount of airflow in order to burn aluminum, to burn that charcoal at a steady temperature. So it's the temperature part.
How about the furnace? How did you build it? Was this your own idea, or did you get some information from a different resource?
This the earth masonry here is inspired by kind of those ancient Adobe brick technology that I have originally seen from a hobby, a hobbyist who practices older technologies.
Now the temperature.
Yeah, I should have it in my references.
Thank you. The
Oh,
temperature
sorry.
required to melt aluminum is very high. What was your safety concerns?
Yes. So first of all, aluminum. Well, first of all, it's when charcoal burns, it can release really hot gas and sparks. So making sure to wear to cover all exposed skin with 1 or 2 layers of clothing is very important. Wear double layering gloves, wearing eye protection, like face protection, just covering everything up. And then after that, once the aluminum is melted, it may create slightly toxic fumes. So making sure to work in a well-ventilated area is very important. I always work outside. After that, it's important to be very mindful of hot surfaces after that. I always it's always important to make the right tools to handle and pour the crucible, so that you don't have any danger of spilling it on any surface, because it will catch anything on fire that it touches. Even on concrete, if it touches concrete, it's going to make the concrete shatter in quite dangerous ways.
Thank you, Thomas. How did you measure or monitor the temperature of the furnace?
I could not directly measure the temperature because I do not have any equipment or know of any equipment that can that can do that. I have heard from Professor Rodriguez that there is a special cone-like material that will melt at specified temperatures. It's what people who work with ceramics use, but I do not have access to that. So instead, I measure it by how brightly it makes steel glow. I know that aluminum melts at roughly when steel glows at about bright red. And then I know if it's too hot, if it gets closer to bright yellow or higher. And I know this because all metals, they glow at roughly the same colors and roughly the same colors based on temperature due to radiative release of heat.
Thank you, Thomas.
And I would just like to just point out, Professor Rufael just mentioned to Thomas in the chat window that at the Photonics lab at Lake Washington, they can help you measure and monitor your surface temperatures. So this is just a perfect example of cross-collaboration and how the presentation of your research really spurs more questions and just opens up everyone's minds to the possibilities of research. Are there any other questions that we might have? All right. Thank you so much, Thomas. Very nice. We very much appreciate you.
All right. Thank you.
Absolutely. And so at 1:55, which is in about 3.5 minutes, we'll have Kylie Dillon et al. Talk about data storage optimization in digital and optical media. And if I'm forgetting anything, other moderators and committee members, feel free to chime in. All right, welcome back again to the Lake Washington Institute of Technology Annual Undergraduate Research and Applied, whoops, I messed it up. The Annual Undergraduate Applied Research and Innovation Symposium. So next we have Kylie Dillon et al. Talking about data storage optimization in digital and optical media. Kylie, you have the floor to introduce your project and the rest of your team members.
Thank you. Hi, everyone. Today we'll be presenting optimizing data storage in optical and magnetic media. My name is Kylie Dillon, and my group members are Sam Wolf, Elena Yao, Taylor Mills, and Jewel Cadado. Our mentors for our research are Narayani Chaudhary and Hani Rufael. So for our research, we combined mathematical modeling studies with photonic experiments to optimize different data storage like a CD, Blu-ray, DVD, floppy disk, etc. Our goals were to maximize data storage while minimizing the storage device size, so mathematically, this is an optimization problem. Here we have two different surfaces. The left is a CD and the right is a DVD. The little marks in the surfaces are little bits of data, which are read from the disk with a laser. You can see that this data on both disks is in almost vertical rows. The spacing labeled above both pictures is what we measured in our experiments. For the CD, we measured the distance to be 1.6 microns, and for the DVD, we measured the distance to be 0.74 microns. Optical data storage is just the use of a laser to read and write from to read or write from a memory device. So we used calculus-based studies to model the data storage and to calculate the CD and DVD arc length and storage densities. We also estimated data storage for Blu-ray discs, and we used laser diffraction studies to estimate the line spacing, which was just the distance from the pictures in the CD and DVD. Here we have a standard disk. The disk has an inner radius of r sub 1, which is equal to 2.5 centimeters, and an outer radius r sub 2, which is equal to 5.8 centimeters. On the surface of this disk, data is stored in a spiral, which can be measured with the equation r equals k times theta over 2 pi. The picture is showing that the same spiral equation using online graphing software. To the right of the picture is the spiral equation, but you can see k is replaced by 1.6. This value is the distance between the lines of data we measured in our experiments. Now our next step is to evaluate arc length and polar coordinates. This is given by the equation s equals the integral from theta 1 to theta 2 times the square root of r squared plus dr over d theta squared in terms of theta. With this integral, we'll be using the spiral equation from the previous slide, as well as the derivative of the equation in terms of theta. We then simply integrate the solved theta 1 and theta 2, which will be using the spiral equation again, but instead of solving for theta, we'll be plugging in the r sub 1 for theta 1 and r sub 2 for theta 2. Our next step is to evaluate the integral, which we can do 3 different ways. One way is to solve this using hyperbolics. Another way is to solve it by plugging in tangent of x for theta and evaluating it by integration by parts. Or we can solve this by completely disregarding the plus 1. Since theta 1 and theta 2 are such huge values, the plus 1 won't make much of a difference anyway. After evaluating the integral, we get the arc length value of 5,378 meters. Now we need to solve for data density, which is given by the equation capacity divided by arc length. The capacity of our CD is 700 megabytes. So we divide that 700 by the 5,378, which gives us 0.13 megabytes per meter. And this slide is just showing that if we had solved the integral using hyperbolics, we would have gotten about the same value for arc length, maybe just a meter or two off.
So I'll be talking about some of the experiments we did at Dr. Raphael's laser photonics lab at Lake Washington Tech. So first we started with Bragg diffraction. We used the red, blue, and green laser sources and pointed it through the CD. So a little bit about diffraction. Diffraction is a wave, or light is a wave, and like all waves, it bends around obstacles. So in this instance, lambda is less than d, lambda being the wavelength, d being the spacing of the two walls, we have no diffraction. When lambda is about equal to d, we have a little bit of diffraction, but when lambda is greater than the spacing, we have proper diffraction. Now, diffraction grating is a large number of equally spaced slits, so it's reflecting off little dots, if you saw in the first image. And this will create constructive interference. So theta, or delta, equals d sine theta, and we can use that to find the spacing on, or approximate the spacing on the CD. And we are looking at first order interference. So here's the wavelength of the red laser. It was 633 nanometers. Here's the wavelength of the green laser. It was 532 nanometers. And here's the wavelength of the blue laser. It was 403 nanometers. So we were able to get 1,558 nanometers for the CD and 739 nanometers for the DVD, which is very close to the actual numbers. Now for the Blu-ray disc, there was no solution, and that is because the observed spacing, 320 nanometers, is less than the lambda, the wavelength. So when you divide d, or theta divided by d, it would create a value greater than 1, and sine theta greater than 1 in degrees is not possible, so we had to change our orientation. Dr. Raphael recommended this paper to us by Alan J. DeVeerd from the University of Redlands, California, about changing our orientation for the Blu-ray disc. So rather than shining the laser through the Blu-ray disc, we diffracted it off the Blu-ray disc at a certain angle. And the incoming ray and the diffracted ray would create different angles, phi naught, phi n. If they were the same, if phi naught and phi n were the same, it would be reflection or not diffraction. But we were able to get diffraction and use the paper's equation of n lambda equals d cosine phi naught minus cosine phi n, and we're able to approximate the spacing. So with the green laser, we were able to get approximate values between 20 and 45 degrees of phi naught. And for the blue laser, we were able to get more values, 20 through 70 degrees of phi naught.
So we also looked into magnetic as another type of data storage, which would be your floppy disks, hard drives, flash drives, and so on. Magnetic accesses information using read and write heads, which are used to detect or modify the magnetization of the material that's going to be directly underneath of it. So they'll be in either an up or a down state, depending on polarity, which is the equivalent to zeros and ones in binary. So magnetic storage uses constant angular velocity as opposed to CDs, which use constant linear velocity. CAV and CLV are the techniques that are used to scan data on rotating storage mediums. The advantage of CAV is that the individual blocks of data can be more quickly accessed, but then the disadvantage is that the amount of data that can be stored on the outer tracks is going to be limited by the storage capacity of the inner tracks. So this here is the equation for the total data capacity of a magnetic storage device, where 2 pi r is the circumference of the innermost track times the linear data density k times the outer radius minus the inner radius all over the pitch p, and that, when simplified, is going to be big K times r times d minus r, where big K is all the constants that were in the original equation. So since the storage capacity of the outer tracks is limited by the capacity of the inner tracks, the question is, when is the capacity of the whole disk maximized? To solve this, since the inner radius is proportional to the outer radius, we can replace r in the equation with SD, where S is a number between 0 and 1 that's going to represent what fraction of the outer radius the inner radius is. So simplifying, we get a times s minus s squared, where a is the 2 pi times k times d squared over p. And then taking the derivative and setting it equal to 0, the equation a times 1 minus 2s is equal to 0, which implies that 2s is equal to 1, or that s is equal to 1/2, which means that the outer radius d should be twice the inner radius r. So what kind of metal should we use for these devices then? With magnetic storage, it's important that the alloy has a good shape for the magnetic readback pulse, and a pulse close to this function displayed on the slide here is going to be the most ideal, because graphically, you can see that the pulse has a neat and clean peak without any additional plateaus, so that you can get a clear reading of whether the read-write head is in an upstate or a downstate without any ambiguity. For example, this is the graphed readback pulse of iron, nickel, cobalt, and you can see that its curve fits very well to that previously shown ideal pulse shape with a distinct peak.
So in conclusion, our studies demonstrated the integrated STEM applications for measuring data storage in optical and magnetic media. It's found that the advancement from CDs and DVDs has yielded higher data storage densities. The Blu-ray discs are able to yield higher data storage densities due to smaller physical structure of the pits that store the data. There's also a challenge in creating these smaller devices, which make it more expensive. We also found that maximum data capacity for magnetic constant angular velocity device, like a floppy disk, is when the outer radius is 2 times the inner radius. And that concludes our project in mathematically modeling the storage in different storage media through photonics experiments. Thank you.
Wonderful, thank you, group. And so we can go ahead and turn it over to any questions that we have. Also, just as an update, we are going to be eliminating the breaks in between the presenters, but I will go ahead and open up the floor to any questions.
We have a question. In what ways do you think you could take this research further to improve current data storage issues?
I know that one goal for data storage is always optimizing it. And the first big step is understanding how storage itself works and finding better ways to make it physically smaller but hold more data. And as of right now, we only know how the current data storage works, but I'm sure that if we took this research further, our next step would be finding ways to optimize that better, I guess, if that makes sense.
Thank you. What was the most difficult part of your findings? Did you guys face any roadblocks or setbacks during your investigation?
We did have some difficulty during our experiment with measuring the spacing of our Blu-ray disc because of the spacing. We didn't have a laser with a low enough frequency to measure the spacing of the Blu-ray with our original setup. That's why partway through, as Sam talked about, we switched the orientation after researching further, and we solved that problem. We didn't really have any other major setbacks in terms of research or any other parts of the experiment.
This might be a fun question for the new generation. What's a floppy disk?
See, I know what a floppy disk is. I'm having a hard time trying to find a way to describe it.
Do you know the maximum capacity in a floppy disk?
I do not. One of my other group members might, though. Like,
I think it's like a couple of megabytes, like 3 megabytes or something like that.
Thank you. Back to you, Michael.
Okay, that just put a huge smile on my face, especially that last part with the floppy disks. Brought me back. Oh my goodness. Oh, that was such a wonderful presentation. Thank you so much. Such amazing work going on here at our university. So I have contacted the rest of our presenters, and everyone is here and present. And so I think that we are going to eliminate the breaks in between. And so these times might change a little bit, but essentially we will still try to stay at around the 15-minute mark for our presentations. And so at this point, I now open up the floor to Elena Yao and her fellow researchers to talk about a mathematical study of real-time solar power data and vector calculus of silicon. You have the floor.
So hi, I'm Elena Yao. I'm with Dave Edward Diaz, Kylie Dillon, Alex Klemecki, and Sam Wolf with a mathematical study of real-time solar power data and the vector calculus of silicon.
so a bit of background to begin with. Currently and historically, our most commonly used sources of energy are fossil fuels, which are non-renewable resources and provide significant greenhouse gas emissions. There's a large and growing movement to swap over to clean energy, which are sources like nuclear, hydroelectric, wind, and tidal. We focused our study on solar energy. Solar energy is categorized as a renewable energy source, and it produces much fewer greenhouse gas emissions than traditional energy sources. The simplified version of the way solar panels work is they're made up of photovoltaic solar cells, which are typically polycrystalline silicon wafers, where when light hits them, the photons knock loose some of the electrons, and it generates an electric current that way.
So silicon has significant covalent bonding characteristics, which is in turn a characteristic of semiconductors. We looked at the charge density of silicon from 3 high symmetry directions with 3D graphing software. So this first picture is along 1, 0, 0, which would be like an axis. The red regions represent high electron density, which fades to blue when there is less electron activity. And then this is the same thing from another direction, 1, 1, 0, which would be like an axis plane. And this is from a third direction, 1, 1, 0, which would be like coming diagonally out from your screen. So just 3 different views of the electron movement. So these silicon atoms have tetrahedral coordination with a lattice constant of about 5.43 angstrom. And any particular silicon set at the origin of a fractional coordinate system will have its 4 nearest neighbors at these fractional coordinates. Silicon is a face-centered cubic structure, which means that one atom is going to be located at each of the corners of the cube and one at the center of each face. So to better understand this crystal structure, we calculated the bond length and bond angle of the atoms. So first, we converted the fractional coordinates to angstrom, which is done just by multiplying them with the lattice constant. And can you go forward another slide? Yeah, so the bond length of the atoms will tell us the force of attraction between the two atoms, and as the length decreases, the strength of attraction increases. So if we think of the distance between two atoms as a vector with a magnitude and direction, then the bond length is just the magnitude of the vector and can be calculated like this, where you square the magnitude of each direction, add them, and then take the square root. So we found that silicon has a bond length of about 2.35 angstrom. The bond angle, on the other hand, is the angle between two atoms, and we used an application of the dot product and found the bond angle to be 109.47 degrees. And depending on the two vectors you perform this calculation on, you may also get a supplementary angle, but it's just a matter of which quadrant you're looking at it from. And this is another 3D view of the crystal structure, graphed using XVoltRaw. So a solar panel will produce the most energy when the light rays hit it directly at a 90-degree angle or perpendicular to the panel. We can use calculus to determine what that vector of that ray would be. For example, this is a problem taken from Openstax Calculus Volume 3, where we have a hypothetical situation where the corners of the solar panel are positioned at these coordinates A, B, C, and D. And we can say the sides of the solar panel are also vectors, so we can find the normal of the plane, which is the surface of the solar panel, by taking the cross product of two of the vectors. So here we took the cross product of side AB and crossed it with side AD, and the result is a vector perpendicular to the surface that's 144 units in the I direction, 0 in the J direction, and 144 in the K direction of this coordinate system. So putting it all together, we also now have the equation of the plane that the solar panel lies on, which is 144 times x minus 8 plus 0 times y minus 0 plus 144 times z minus 0 equal to 0.
Here we are given the unit vector S, which points toward the sun at a particular time of the day. The flow of the solar energy as F equals 900 multiplied by the unit vector S. We need to find the predicted amount of the electric power the panel can produce. And to do that, we need to find the dot product of F and N. To find the dot product of two vectors, we need to multiply the corresponding elements of each vector and then add the results together, as expressed in this solution. And we got 149,649.19 watts. And we are asked to determine the angle of elevation of the sun above the solar panel. We are also told that the angle between the normal vector and the unit vector S and the angle of elevation are complementary, meaning they add up to 90 degrees. To do this, we need to first find the angle between the normal vector and the unit vector S using this formula. Cosine phi is equal to the product of the two vectors and over the magnitude of those two vectors. And we got 35.26 degrees. Since the angle between the normal vector and the unit vector S and the angle of elevation are complementary, we can just subtract 35 from 90 degrees and we got 55 degrees as the angle of elevation of the sun.
Since power is the derivative of energy, we can use the first fundamental theorem of calculus to find energy produced over a given period using a power versus time graph. We can integrate from T1 to T2, and the area below the given power curve is the energy produced. Real-time data from solar panel grids are currently available on internet databases. We determined the total energy produced by a solar panel array over the course of the day by finding the area under the power versus time graph. We analyzed the data using integral calculus-based methods. This one sample graph from January 19th from Bryn Mawr College in Pennsylvania. We used Excel to find Riemann sums as well as to approximate the graph with a polynomial. We then integrated that polynomial to find the area in a different way and to double check our work. The total energy produced on this day was 11.2 kilowatt hours, or approximately 4 times 10 to the 7th joules.
Our studies provide us an atomic level understanding of solar energy, its technology, and applications. This project was a practical application of an integrated study and cross-collaboration with math, physics, and engineering.
All
And
right.
that concludes our presentation.
Wonderful. And with that, we will open up the floor for any questions that anyone has for the presenters. And while people are potentially gathering their questions, what I would like to do for just a moment is to go ahead and acknowledge Dr. Amy Morrison, who is attending our symposium right now, the president of our university. So welcome, Dr. Morrison.
Hello, nice to see you all and hear a little bit about all of your great work. So I'm just here in my office working on a few things and just ever impressed by the work of our students and faculty. So thank you so much for the invitation today.
Thank you so much, Dr. Morrison. We're so happy to have you. All right, looks like we have some questions for the presenters.
Here's the first question. Is the data on the rate of energy production available to the public?
By that, do you mean like how quickly or how much energy solar panels are able to produce within a given amount of time?
Yes.
Yeah, I'm talking about the numbers you were integrating.
Yeah, so those numbers were from the university's publicly available database so it basically contained how much energy their solar panel arrays collected within each day, and then they list the amount of energy per day. So that's where we got those numbers from.
Okay, I see.
We have a comment from Narayani Chaudhary. She wants to share that this is an open energy database. Anybody can use this data. So it's available to public. Another question, what kind of polynomial was used to fit the power data?
So when we input the values, the values were listed over 15-minute intervals. So we input those into a table, and then we used the ability of Excel to approximate a polynomial, and we generated that to, I believe, a 4th order polynomial, and then we integrated that.
Thank you. Narayani Chaudhary wants to add that regression analysis and Excel was used to solve the polynomial. Thank you all. Over to you, Michael.
Thank you very much, Priyanka. All right, and so next up we have Sam Wolf et al. Talking about data encryption and scramble using mathematical methods. And so Sam, without further ado, you have the floor.
All right, thank you. So hello, everybody. This is data encryption and scramble using mathematical methods. I'm Sam Wolf. The co-presenters are Lena Yao, Kylie Dillon, Alex Kalemecki, and my mentor is Dr. Narayani Chaudhary, and we're from Lake Washington Tech. So data encryption is very important in cybersecurity. Most modern encryption systems use some form of matrix algebra. We developed a phone app that uses data encryption. And we also looked into encryption methods suitable for text, audio, and image. These are applied uses of static and dynamic encryption.
So to start out, let's start out by answering the question of what is a matrix? A matrix is just a rectangular array of items arranged in rows and columns. When transposing a matrix, you just switch the rows and the columns. As you can see here, matrix A is originally a 3x4 matrix, and after being transposed, it becomes a 4x3. Next slide, please. So when multiplying the matrix by scalar, you just take any matrix of any dimension and you multiply each value in that matrix by the scalar given. You can see here that the scalar value is 5 and each value in that matrix is multiplied by that 5. Multiplying two matrices together, however, is not as simple. Here we start with matrix A again, a 2x3 matrix. To multiply matrix B by A, the dimensions of B has to be 3 by something. By that I mean the number of B's rows needs to be the same number as A's columns. Matrix B's columns, however, can be any number. This is because, as you can see, we start out with 1 times 5, then we add that to 2 times 6, and we add that to 3 times 7. We repeat this with the first row of matrix A and the second column of B, and continue with row 1 of A until there are no more columns in B. We then repeat this process with the rest of the rows in A, as shown for matrix C, and the product, which is the product of A and B.
Each matrix has a determinant, which is just a characteristic number of the matrix. The determinant can be found by multiplying, in this example, A1 times B2 and subtracting B1 times A2. You can see in the sample matrix C, the determinant that results is -7. You can find the inverse of a matrix by multiplying the reciprocal of the determinant and switching the sign of B1 and A2. To find the inverse matrix of C, we would divide by -7 and switch the sign of the 2 and the 5. And for doing this, with anything larger than a 2x2 matrix, you should use a computer. A singular matrix is one where the resulting determinant is 0. If the determinant is 0, then it has no inverse either, since dividing by 0 would just return an error.
So we'll be going over encryption methods for 3 types of data, which are text, image, and audio. So static encryption, how to encrypt data. Static encryption is where each key of a keyboard is represented as a unique number so that we can carry out mathematical operations on them. For example, lowercase a through z can be 1 through 26, period is 27, space is 28, and other special characters can be 29 through 99. Just converting letters into numbers on its own isn't very secure, so since anyone who intercepts the message can easily directly convert the numbers back into letters as long as they have the cipher table. So the message is placed into a matrix and a key is used to add another level of security by encrypting the message and turning it into gibberish that only a party who knows the key can use its inverse to undo the operations and decrypt that data. For example, this is a 2x2 matrix key. It can be applied to this 2x3 matrix that represents the word space. This matrix P represents the word space, where the letters were replaced with numbers according to the cipher table. Then, using matrix multiplication, a new matrix is formed from the product of the key matrix K multiplied by P. This matrix is then sent over, and when we apply modulus 29 to the numbers in the new matrix so that the range of the numbers is once again within the range of the cipher table, Then decoding against the ciphertable SPACE has now become JHIOE, which is meaningless. Only someone with the key, which would be the intended recipient party, can use the key inverse on the matrix sent over and decrypt it back to the original matrix, which represents space. The previous example used a symmetric key algorithm, but it relies on both the sender and the receiver keeping the key a secret. This process is further complicated when you have more than one receiver or if the key gets changed a lot. There are ways to further enhance the security using modular arithmetic and secret and public keys. So both parties decide on a modular number to use, and it doesn't matter if this number gets leaked out. Here, 29 was chosen because 29 is both prime and outside the ciphertable, so it can be evenly modular within the table and will produce a singular matrix. Then we have a secret key that no one but the recipient knows, so they don't have to take the risk of sharing it anywhere with anyone else. Then there's a public key that has a coefficient determinant of 0, so that the public key won't have an inverse. It doesn't matter if anyone who intercepts the message has this key. This is because the secret and public keys are combined to make a new key. Key K is AGA inverse mod P, in this case P being 29. And now that we have a key, we want to encrypt the plaintext AD. So referencing the ciphertable, AD becomes a 2x1 matrix we will call M, that is 1 and 4. Next, we take the product of the key K and plaintext M and add an additional random vector layer and end up with a matrix C that hosts their ciphertext NZ corresponding to plaintext AD.
All right, so this is Felix the cat. It is a 35 by 35 matrix where each black pixel is represented by 0 and each white pixel is represented by 1. One way of encrypting the image is transposing it. Like Kylie mentioned earlier, we swap every row with every column. The effect would be similar as if you were grabbing the top left-hand corner of the page and dragging it to the bottom right-hand corner of the page while flipping it over. Another way of encrypting the image is with parametric equations. A equals the matrix representation of Mona Lisa, and Z equals the matrix representation of Lego Mona Lisa. We can model a parametric equation and determine what percentage Mona Lisa is truly being shown. For more advanced images, we can use grayscaling to define more values that adds more security. 0.1 for a dark gray, 0.5 for a normal gray, and 0.9 for light gray. RGB images also follow a very similar process. Sounds can be encrypted when the air vibrations that are captured by a microphone are digitized. One method of digitizing sound is a wave file. It stores a digitized value for each point in time. Now let's look at some more advanced encryption systems. Dynamic encryption is similar to static encryption, except there is a random number added in that only the sender and the receiver know about. This random number can be based on anything like the time of day or the location of the sender. Here's some images of the iPhone app that utilizes a basic form of dynamic encryption. It sends and receives to itself, but it can encrypt the 0 through 28 encoding values to be something very different, such as a number in the 10,000. Another system of encryption is data scramble. It will randomly shuffle rows and columns in a certain path. The receiver takes that path and reverses it to get back to the original matrix. When financial data is being sent, a secure system is needed. A commonly used system is AES, or Advanced Encryption Standard. It uses end-to-end data encryption, which involves several new mathematical algorithms. So here's a little bit of like a story problem. So now let's assume there's a customer trying to send information to their bank. There will be multiple nodes that it will pass through. You can think of each node as a server handing off data to the next server. The data is encrypted with 4 different keys using matrix multiplication. To decrypt the information, each node multiplies the inverse of the key in reverse order. Remember that matrix multiplication is not like regular multiplication. Order does matter. This is very secure since if an attacker were to breach any of the nodes or the servers, the information they would have is useless. With all these encryption methods in mind, we can build a large, complex encryption system. We can transpose a matrix, then statically encrypt its values, then add a data shuffle with 5 layers of end-to-end encryption, then dynamically encrypt these values based on the time of day and location, and have a public and private keys to protect this final key. Linear algebra is essential for data encryption on computers. Its methods are suitable for simple or advanced systems. This project has been a great hands-on experience for applying both math and computer science to the real-world scenarios. And these are the references of this project, and that concludes this presentation.
And with that, we'll take a minute or so for the questions to roll in.
Thank you, Sam, Wolf, and team. We have no questions. Over to you, Michael. Oh, we have a new one. Just wait. You mentioned earlier that there were both public and private keys used to further enhance encryption. What is the advantage of using these?
Okay, so starting with the first question. So public and private keys, if you have one key that can break the matrix, then that can be a problem. But if you have a public and private key, you can think of it as a key and a lock, and they're separate. So they need to go together in order to break something. And usually the public key will be a singular matrix, meaning it has no inverse on its own. And the only way to decrypt the information is with both of them paired together.
Thank you. Another question. Today's government use sophisticated methods to code messages. What kind of a matrix-based code would be very difficult to break? How large would be the matrix?
Now, I don't know how large the matrix would necessarily have to be, but I do know that end-to-end encryption, like the bank, for example, where there's multiple nodes that it would hand off to, is very common for data, for financial data, so very secure systems. So the governments would probably utilize something about that level, where each key is multiplied in a certain order and then decrypted in that order. So there is a key of keys, if that makes sense.
Thank you. One more. Are invertible matrices ever used to encrypt data?
I'm not exactly familiar with invertible matrices. Did you mean inverse matrices?
There is a correction in that question. Not invertible matrices.
Not invertible. Meaning matrices that have no inverse?
Right.
So there would be no point to that, because if there's no inverse to it, you would encrypt it, but then never be able to decrypt it. So no, there would be no advantage to using that. Only if you wanted to scramble data to throw off an attacker.
Okay.
Thank you. Over to you, Michael.
All right, thank you so very much. That was so very interesting. So very interesting. At one point, I wanted to just put into the chat, cool. All right, I'm loving it. Thank you so much, everyone. Thank you, presenters. Thank you for everyone asking your wonderful questions. I also want to just thank the presenters for their flexibility in changing their times. So obviously, right now, it is not 2:55 p.m. However, Jordan Acosta and his group on the simulated lunar rover project have agreed to just go ahead and continue so that we maintain a nice flow for the symposium. So Jordan, You have the floor whenever it is that you are ready.
Thank you, Michael.
Actually, I think Jordan doesn't know what's going on, so I
Oh,
got
there
this,
you go.
Jordan. My name is Colin Williamson. I am the lead designer and manager for the Simulated Lunar Rover project. Our team consists of Shane Niemela, who leads the mechanical design and fabrication, Denny Hofer, who leads the electrical design for power systems and module resources, Hiromo Pulido, who leads PCB design and fabrication, Jordan Acosta, who heads documentation as well as the charging station design, and Tarek Youssef, who heads procurement as well as documentation. And we are under the supervision of Dr. Andy Rofio. The research and development objective of the Simulated Lunar Rover project is to justify the role that rovers will play in the future of manned missions beyond Earth's orbit, particularly targeting the growing interest in missions which build permanent establishments on the moon. With that as a scenario, we wanted to consider what rovers what rovers do really well that would be useful to the astronauts of such a mission, or perhaps things that rovers could do really well but never have had the demand for it in the past. So we came up with two major points. One, astronauts exposing themselves to space represents a lot of risk. Two, astronauts performing tasks that robots can do is a waste of their time. It's very expensive to send people into space. In combination, astronauts exposing themselves to risk to do basic tasks is highly undesirable. And that is how we are justifying the use case for rovers on potential future manned missions. So we're talking about tasks such as exploration, hauling, simple construction tasks, deployment of science payloads, or data collection. What we've proposed here is sort of like a Swiss Army knife kind of rover, which excels in being robust, mobile, configurable for many different tasks, and overall being a workhorse and carrying a lot of resources. Because at any point that a rover can supplement an astronaut or enhance an astronaut's productivity, the risk to that astronaut is being minimized as their EVAs, their extravehicular activities are shorter or fewer in number, and their time is better spent doing things that only humans can do, which is why we send them into space to begin with. And there is a good reason to design a rover to be as multi-purpose as possible. The best tools are ones that are always close at hand and useful in many situations. If you send up rovers that had only very specific tasks they were capable of, then a bottleneck of demand could potentially be created where a given task, for a given task, the best tool is likely not nearby, so the rovers won't be used because, well, they're being used elsewhere by someone else. In space, where nearly everything takes longer and more steps to do, you need tools that are available when they are needed, and that follows the principle of when NASA designs what types of tools to give astronauts on their EVAs. They're often highly versatile. So this may sound like a really tall order with a lot of design complexity and failure points, and to some extent it is, but not as badly as you may think. The key to building a system like this is building a modular standard into the design. In this case, we have designed a standardized system for reconfiguring the features of a rover via modular bays. If you look at the main diagram at the top of the poster, each one of it's a bit hard to read, I understand. The yellow boxes, those are all modular bays. They can be swapped out with anything that you can think of creating that meets the standards and can operate under the resources that the rover can provide you. So these slots are a lot like drawers all around the rover body, which have all the same resources of power and data connection. So say you want to introduce a new sensor package for a science experiment that measures ultraviolet light intensity on the moon. It's as simple as adhering to that standard set, integrating it with the module and plugging it in. The rover will send power to the module, and the rover computer can be queried for the data that the module is producing. Now, I'm going to move on to the mechanical side of the rover. Well, that was partially mechanical, but talking about, we took a novel route in our design of the drive system and overall motion characteristics of this rover. What this design attempts to do, and which we have yet to test and confirm its efficacy, is duplicate the all-terrain capabilities and merits of the classic six-wheeled bogie design common in the Spirit and Opportunity rovers. And we do this with a four-wheeled rover design. And we feel that there is great potential for the system to be even more capable than the standard six-wheeled design that people are familiar with. What we have made is a system where the four rover wheels are on arms, two arms on either side of the vehicle, two sets of arms on either side of the vehicle. The arms meet each other in pairs, forming an A-frame, and at the top of the A-frame, it connects back into the main rover body. And the result is that the body hangs from these arms like a cradle, giving the vehicle a very nice low center of gravity. There are two, there are two further systems that give this design its special capabilities. The first is strong motors in the shoulder that can rotate the A-frames independently. This allows the rover to angle itself in pitch, but also shift its center of mass. And the last system is the rail system, and that is the purple slide assembly you see in both those drawings. A further two linear motor systems in the body of the rover move the A-frames along the body back to front and also independently. What this allows the rover to do is to traverse nearly any type of terrain, roughly emulating the motions of a quadrupedal walker type robot. It is also capable of self-riding and climbing ledges in this type of configuration. And as a bonus, due to the extra degrees of freedom in motion, it allows for very fine motion control for tasks such as the rover's topography scanning module. You see that in green with the at the bottom of the rover there. The topology module, where the rail systems and the drive motors work together to create smooth linear motion. To create scanning maps of the surface below it. While yes, this is a very complicated design with a lot of failure points, remember that these rovers are not intended, as with previous rovers, to operate their entire lifetime alone. That being said, this design is also robust against many singular failure types. The rover can maintain a majority of its mobility after failure of any one drive wheel, because it can angle its drive wheels and then drive on 3 wheels instead of 4. Any one steering motor and any of the shoulder and slide systems, as they only enable the rover to scale extra difficult terrains, they are not absolutely essential for it to manage to get back to base and be repaired for any fault failures. The hope is that all this culminates into a rover that is at least as mobile as an astronaut on the moon. And those spacesuits, I don't feel like it would be that much of a stretch to have a robot be able to go as fast as a human on the moon. This project is not yet finished. Currently, the mechanical fabrication of the major systems is nearly ready for basic motion testing, and this will test the rover's modes of mobility by rating the actual performance capabilities of the motors and custom designed mechanical systems like the shoulders. The design of this rover had to be divvied up into steps for practical reasons. And the next step we will be tackling starting this summer, and will involve internal organization of the rover, its pull-out modules, and will involve developing further computer and sensor systems and getting the remote communication system operating. That will make development much more easy to accomplish on the software side of things, because we'll have a way of doing useful tests against the hardware. How am I doing on time?
So you are at about the 10-minute mark, and so we're doing pretty good on time.
I think actually, yeah, I'll leave it there. I could go into more, but I think that's a good place to leave it for questions. I have a mechanical design lead, electrical design lead, and documentation team members here to answer specific questions about those.
All right, and with that, we will move over to the questions portion. So go ahead and take a look at the poster. I know it's kind of hard to read the poster while the presenter is talking. So take a moment, take a look at the poster, enter any of your questions into the chat.
Here's the first question, team. How many different departments came together to make this happen?
We started off reaching out to many different departments. We reached out to machining, the innovation lab, not technically a department, but also welding department, and collaboration was promising in the beginning, but we ended up going for full in-house fabrication in the end, with some use of the innovation lab.
Have you considered contacting other universities that are working on this, like the University of Colorado?
You know what? I'm surprised that we have not actually thought of that. We have seen other commercial efforts for designing rovers, such as a Mercedes rover, but we were very heads down.
Thank you. So another question is on the semi-autonomous nature of the robot. What kind of task would the rover need to do autonomously, and how would it do them?
So this gets into the second portion of development that we will be entering into the summer. The plan is to implement obstacle avoidance and pathing. We will be utilizing an array of time of flight sensors. They're not shown here on these diagrams because there will be a lot of them covering every extended edge of the rover. These time of flight sensors will provide the rover with a clear understanding of where it will fit through and what its pathing opportunities are. We're still selecting a mode of algorithm or AI to drive the pathing itself, but it's a large ecosystem to choose from. Other autonomy that would be nice to have is, and these are coming out in open source packages, very well packaged these days, are things such as facial recognition and gesture recognition. So the rover could potentially identify a user, and they could flash a hand signal at the rover, and the rover would know to try to follow them or do something like that. Those are more of our stretch goals.
Thank you. Another question regarding the arm assembly. So is the arm designed to open up and extend?
The arm is also a suspension system, so it is not meant to operationally open. It is supposed to be a static A-frame, but there is a spring loaded suspension system so that if the rover takes a hard fall, it does bounce instead of break. But the way in which the arms rotate is that the entire A-frame, both wheels rotate at the same time, but they rotate independently of the opposite side of the rover.
And are the arms connected so they rotate in the same direction?
No, they can rotate independently of each other. The A-frame is static. The A-frame itself rotates independently of the A-frame on the opposite side of the rover. There is a maximum limit because they are wired of about 360 degrees in any one rotation before it has to go back to neutral. However, this is what allows the robot to flip itself from an upside down position, recovering from being tipped, or orienting its sensors in virtually any direction.
Thank you. Michael, back to you.
Thank you very much. That was wonderful. So much appreciate that.
Oh, I think we have one last question.
Oh, please go ahead.
Someone by the name of Hanny Raphael asks, what does space L stand for? Very good question. Space L is our fictional company name. That if we were a space technology contractor, our name would be Space L, and the L stands for Lake Washington.
Very nice. Definitely bring the credit home. Good job, everybody. Wonderful. All right, so we're going to go ahead and move on. And so Gloria McGillis has prepared a presentation on a really great idea for a remote control prototype. So Gloria, you have the floor.
Hi, thank you for having me. Okay, and go to the next slide. So the problem started the first time I stayed at my husband's place alone when we were still dating. The 5 remotes on the right were on Jerry's coffee table, and I had no idea how to even turn on the TV. For years, I have only had 2 remotes, one for my TV, the other one for Apple TV. Jerry has 5, TV, speaker, Fire TV, DVD player, and a fan. When I want to turn down the sound, I have to use the speaker remote. And when I need to turn on the TV, I use the TV remote. And when I need to find things to watch, you get a picture. Eventually, when we moved in together, I bought a LWTech universal remote, hoping it would simplify our lives. However, Jever never learned how to use it, and now we have 6 remotes sitting on our living room table, 4 in the bedroom. That's a total of 9 remotes. Next. I think it's now safe to say that we need to do something about this. The universal remotes definitely helped me, but not Jerry. And even for me, it was a painful process. I had to use an app to program the universal remote, which was very time consuming. Because once I made a mistake, I had to start over. In the book of Design with a Mind in Mind, Jeff Johnson suggests that when risk is low, we explore more and learn more. This is not the case with the app. I felt forced to program the remote because I had already paid for it. If the app would easily allow me to go back a step when I made a mistake, it would not take me all day to program the remote. If the remote didn't have so many unnecessary buttons, maybe Jerry would be willing to learn it too. Because of this terrible experience, when we get a new device, I would be less likely to add it to the remote. And next. To eliminate the number of remotes, I have decided to dedicate this project to design a better universal remote comparing to what's on the market currently. Many people still enjoy a physical remote because it allows them to touch, feel, and physically push a button. Instead of having to find their phone, look for the app, find the device, and finally arrive where they want to be, a well-designed remote allows the users to arrive at their destination within a couple of seconds. Its minimalist design, as few buttons as possible, will encourage users to explore its possibility and accomplish more with one simple device. Most households are using multiple remotes to control one experience. If we can figure out a way to combine all these remotes effectively, this could simplify device management and reduce electronic waste. A small remote isn't as big as a TV when it comes to waste, but we can start small and maybe this will become something bigger. Next. To explore how the remote should look and feel when held with a hand, I decided to order some modeling clay and experiment with it. I first came up with this small half avocado shape. It fits right in your hand. You can push every button by just moving your thumb. I then thought it wouldn't lay evenly on the table, so I stretched the top to make it curve and extend down onto the table. Well, this is an interesting shape, I thought. After a long period of time holding this model, I started to create a dent on the back where my index finger is. The dent is here to stay. Next. In order to have fully customizable buttons, the icons must be adjustable by the users. So I thought, why can't I just make the buttons tiny screens? They should change depending on what you press, so they can control up to 5 groups of devices. Although there are just the 5 buttons, if they are dynamically adjustable, it makes this little remote so much more powerful. Next. Home device icons are difficult to understand. They're not as universal as the icons we use on websites. I can only try my best to come up with good icons, but I can never ask the users to remember what each of them means. So how do I make sure the users know what they are controlling at all times? I then decided to combine letters with icons. For example, the fan icon with letter L means living room fan. However, in a tiny scale, none of those icons were readable. Then it hit me, if the user is trying to operate buttons, they aren't currently interested in talking to Alexa. So why don't I turn the Alexa button into a feedback display so that the user could have the full clue until they build up muscle memory. The return button is always there, so the user can easily go back and engage with Alexa again. In this case, the LED light can't always be blue when we're navigating smart home controls. I then did some Alexa color signal research, which you can see here. I incorporated them into my design. Next. Here's the technical drawing of the remote. The remote would not have pre-printed icons for customization. Next. Buttons are slightly indented to fit the curve of a finger. They feel like buttons and act as tiny screens that can be customized any way you wish. Additionally, these buttons work with the feedback screen. Whichever finger is hovering over, the feedback screen will give the user 1 to 3 keywords of what that button is for. Next. Direction keys are in the, on a traditional remote, they are useless when something is playing on the screen. But on my remotes, they can be used to skip, rewind, and adjust volume. This should be very intuitive and it saves precious space for customizable buttons. So press left or right to skip or rewind. Press and hold to activate the process bar. The ring represents the process bar from beginning to end. Move your finger along the ring to go to the exact location. Let go when done. Press twice to skip or rewind chapters if the device supports it. If not, this action will make the process faster. And similar rules applies to the volume control. Next. Originally, I only came up with 5 groupings. Since my buttons are not all displays, it makes the possibility endless. If the user wishes to control more than 5 devices, the last button could turn into a next button. Now this remote allows up to 9 customizable grouping controls and 3 layers of nesting control. There's a limit only because I don't want to overwhelm the user. This graph is showing an example of how this particular user set up their remote, assigning which device and preferred shortcuts they desire to control. Next. Finally, my final remote shown here is completely black with a matte finish for non-distracting screen time. The curve in the back allows for easy pickup off of any surface. And it's charged wirelessly by any Qi certified charging pads. Its organic shape makes it comfortable to hold. The size is small enough for a thumb to travel from bottom to top without having to reposition the remote. The index finger rest will also keep it stable in one's hand. All buttons except the power buttons are indented inward for comfortable touch. The navigation button ring has a glossy finish. It's flat and raised to the surface, so a thumb can comfortably move along the circle to control volume or skip and rewind. All displays and illumination will be turned off until it's picked up. This remote will not be easy to lose because of its size and unique shape. However, if lost, its companion app will make it sing a pleasant song. If you're interested, you can go to this video and watch my live prototype. And next. So in conclusion, the universal remote that are currently offered in the market are too limited in capability or requires the users to remember their own button setup or voice commands. Their design are either too simplistic or too complex. Additionally, tactile sensation is important for muscle memory. My remote utilize sleek intuitive design with fully dynamic icons and feedback that adjust based on the device you're trying to control. Next. Here, my remotes, yeah, this is my remote compared to the remotes currently on the market. And thank you for listening.
Gloria, we have some questions.
Yeah.
Since this is a touch screen, would you be able to add haptic feedback so users know when they press a button?
I'm not sure what haptic means, but so whenever you are hovering your finger on a button, the feedback screen will tell you exactly what you're about to enter. And if you move your finger away, that would disappear.
Okay, the next one. Who is your mentor for this project? Love the concept, so do I. Are you planning to bring this idea to life and try to make this device?
I would love to bring this to life, but I'm not sure if the technology is there yet. However, I did have a little graph of how the buttons should work. So basically you have buttons on top and underneath it's just a one piece of touch screen like a phone, you know. So you interact with the buttons and then your little display will tell you what it is. My mentor is Steve Ader, and he had the same problem as me that has too many remotes laying around in the house. So he was like, you know, you should get this produced.
I agree. A quick question. Are you aware of Elgato Stream Deck? I know that they have similar design for buttons with screens that are customizable.
No, I have not, but I will check it out.
Another comment. Part of this limitation is caused by companies wanting remote control to work only for their own products, not their competitors. How would you expect a universal remote to work with products made by other companies that compete with each other?
That's a good question. I never thought about it that way.
Okay, there's another.
Yeah, I think The universal remote I bought at home, the companion it's called, that one is actually the most useful. However, it's just way too many keystrokes. So I don't think it's a problem that you can make a remote that works with all of them. Yeah, as long as their other company is not stopping you to do that.
Mm-hmm. There's another question on user interfaces. Have you ever used user interfaces before or made any other prototypes?
So my background is a web designer. I just wanted to explore a physical thing, and I'm glad I did, because this actually turned out much better than I thought. As a web designer, this kind of is a interface in a way, especially when I turn them into little displays. So I think my background actually contributed to this, but yeah, in the future, I would like to build an app as well, like how to set up this and, you know, that sort of thing.
Yeah, Gloria, and you have an invitation from computer software department. They would love to work with you and give you some options for the software.
Oh, awesome, thank you. You said, who is it from?
Jesse, computer software department.
Oh, I see. Oh, nice.
Sorry,
Okay,
let
thank
me
you.
restate the program's name. Computer Software Development Program.
Oh, I just saw that comment. Awesome. Thank you. Thank you, Jesse.
Thank you all. Back to you, Michael.
Great, thank you so much, and thank you, Jesse. So that just points out, again, as I'm standing on my soapbox talking about the importance of these conferences and these symposiums. You know, these aren't just for you to have a chance to stand up and say, hey, look how amazing I am. And by the way, Gloria, that was pretty amazing.
Thank you.
It's also this really great opportunity for you to network with other people in your field and in other fields. And, you know, collaboration is the way that science proceeds. And so this is phenomenal. Yes, this is, it's great to see doors opening and collaborations happening. So I'm very, very excited. Thank you so much. So we'll go ahead and move on to the next presentation. Dave Edward Diaz et al. And Elena Yao are going to talk about the calculus of clovers, and they have agreed to be flexible and go a little bit ahead of their scheduled time of 3:35. So after they are finished with their presentation, I will just have a few words to say and we'll wrap things up. So Dave Edward Diaz, you have the floor.
Thank you. Good day, everyone. My name is Dave Edward Diaz, and I'm joined by my partner, Alana Yao, and we're going to be presenting the calculus of clovers, and our mentor is Dr. Narayani Chowdhury. So the cloverleaf is a fundamental shape that manifests often in nature, and we have some examples of that we're going to show you. So the transfer-ribonucleic acid, or tRNA, is a type of RNA molecule that helps decode a messenger RNA or mRNA sequence into a protein. Those proteins are built from smaller units called amino acids. The tRNA molecule has a distinctive folded structure with 3 hairpin loops that form the shape of a 3-leafed clover, and it's measured at about 26.4 nanometers in length. Here we have a picture of the 5D orbitals. In atomic theory, an atomic orbital is a mathematical function that describes the wave-like behavior of electrons into atoms. The general shape of the d orbital is a 4-leafed clover. These orbitals are important in the transition metals because they are typically used in bonding, where they can easily give and take off electrons. And what we have here is the satellite picture of a cloverleaf interchange that can be seen at the 85th Street in Kirkland. A cloverleaf interchange is a 2-level interchange in which left turns are handled by ramp roads. The objective of the cloverleaf interchange is to allow 2 highways to cross without the need for any traffic to be stopped by red lights. And finally, we have the Cloverleaf Quasar. It is a single object whose image has been reproduced 4 times in a cloverleaf-like arrangement through the process known as gravitational lensing. Thanks to the Chandra Observatory X-ray telescope, we are able to view this picture of a quasar 11 billion light years away, and it provides the evidence of a large-scale star formation in the early universe. Now, after those examples, we're gonna show you how we develop the mathematical models resembling the cloverleaf shape. And we have used multiple integration involving double and triple integrals in polar and cylindrical coordinates to calculate the areas and volumes of these shapes. Now what we have here is a shape called Rhodonia, which was named by the mathematician Guido Grandi between 1723 and 1728. It was named Rhodonia because it resembled the shape of a rose. The polar equation of this shape is r equals a sine n theta, where a is just a scaling factor of the shape and n is the determining factor of the petal. If n is odd, the shape is n petaled, and if n is even, the rose is n petaled. We can see that if n equals 2, the shape is 4 petaled rose, and if n is 3, which is odd, it will be 3 petaled rose. So you too can experiment on plugging numbers to the variables here in Desmos. It's an online graphing tool. You can see how the shape of the curve would change depending on the numbers you would plug in. Okay, and now we move on to the polar coordinates. The polar coordinate system is formed by fixing a point O, which is the pole or the origin. And the polar axis is a ray constructed from point O. And each point P in the plane can be assigned the polar coordinates r theta, where r is just equal to the directed distance from point O to P, and theta is the directed angle measured counterclockwise from the polar axis to segment OP. Next, please. One more. One more. Okay. So, and here we have the polar parametric equations. X equals r cosine of theta, y equals r sine of theta, and tangent of theta is equal to the opposite side over the adjacent side, or y over x, and r squared equals x squared plus y squared. To transform the Cartesian to polar coordinates, we need to evaluate the determinant of the Jacobian matrix. And we need to use these parametric equations, x equals r cosine of theta and y equals r sine of theta. And this is how the Jacobian would look like. The determinant of the Jacobian matrix is equal to r, and this can be used to transform integrals between the two coordinate systems. But why do we have to transform the Cartesian to polar coordinates? It is because the polar coordinate system is easier to use with rounded geometry. So similarly, to transform 3D Cartesian to cylindrical coordinates, we have used the same procedure, but now we have an added variable, which is z, and it tells us the height or the depth of the stuff that we are measuring. And this is how the Jacobian matrix would look like. And we have solved the determinant, and we will get r. The area elements, or dA for Cartesian, is dx dy, or dy dx. In polar, it is r dr d theta. And the volume elements, or dV for Cartesian, is dx dy dz, or however you want to put that in order. And in cylindrical, it is RdZ drd theta, where the R is a variable that we got from the Jacobian matrix that we got from earlier.
So what we have here is a problem from Openstax Calculus Volume 3, where we will put those previously mentioned concepts to actual use. So here we want to know the area of this four-leaved rose that is equal to the region enclosed by the equation r equals to sine of 2 theta. This problem can be simplified thanks to the symmetry of the petals. Because the petals are all equal in area, we only need to calculate the area of one of the petals and then multiply it by however many petals there are, which in this case is 4. So our double integral to calculate the area is a equals to 4 r dr d theta. Can you just click once? Where the bounds of the inner integral are from the point of origin to the edge of the petal, which would be from 0 to sine of 2 theta. And the outer integral will be for the first quadrant only. That is where the first petal resides, which is from 0 to pi over 2. And then solving, we get that the total area enclosed by this particular 4-petaled rose is pi over 2 square units. Next, we can look at a real-world application of these concepts. This is also a problem from Openstax Calculus Volume 3 of a clover-shaped swimming pool. The edge of the petal portion of this pool is defined by r equals to 10 sine of 2 theta, and the depth of the pool, which is also the height of the pool, is simply z, which is equivalent to x plus y feet. And we graphed that equation r equals to 10 sine 2 theta in Desmos, so this is what it looks like from an overhead view. So to find the amount of water this pool can hold, or the volume of the pool, we set up the triple integral v equals to r dz dr d theta. And once again, because the petals are identical, we only need to find the volume of one of the petals and then multiply it by the number of the petals to get the total area of the petaled portion of the pool. So our triple integral is then v equals to 4 r dz dr d theta. The innermost integral will have the bounds for z. The lower bound is the minimum height of the pool, which is 0, while the upper bound is the maximum height of the pool, which is z, which is equal to x plus y. That means that in cylindrical coordinates, z, or the upper bound, is going to be r cosine theta plus r sine of theta. And the middle integral's bounds are from the origin to the edge of the pool, which is from 0 to 10 sine of 2 theta. And lastly, the outer integral's bounds are once again from 0 to pi over 2 for that first quadrant. And after solving this triple integral, we came to the conclusion that the pool would be able to hold about 1,219 cubic feet of water. And this was just the work that went into solving that triple integral. So next, to find the average depth, or the average height of this pool, we once again calculate for the area of the surface of the pool. And since the average height can be found by dividing the volume by the area is found to be 157 square feet, which makes the average height of the pool to be 7.76 feet. And once again, that was just the calculations. In conclusion, the Calculus of Clovers has many applications in fundamental sciences, engineering, and transportation. For example, we can apply these concepts to find the mass of that Chandra Quasar, or the amount of land needed to build the Kirkland Highway interchange. We showed how multivariable calculus studies using polar and cylindrical coordinates help to unravel the characteristics of these shapes. And that concludes our presentation. Thank you.
Thank you very much. And so we will open up the floor for questions.
This question is regarding d orbitals. Would you use spherical coordinates to calculate the volume?
No, actually, so the shape, the d orbitals are actually showing the path of how the electrons are moving. So there's no real volume. It just shows you the path of how the electrons are moving around the atoms.
What about the arc length for the d orbital?
Yes, certainly. You can use integral in calculating the arc length of those of the path that the d orbital looks like.
Thank you.
All right.
Michael, back to you.
Great. So thank you so much for all of our presenters and all of our participants. I also can very much appreciate the fact that we have roughly the same amount of, we only lost a few participants along the way. But just to let you know, we will be awarding certificates to all of our presenters, and that certificate will have the name of their project and their name, and it will be signed by the president of the university and will be presented to them in some sort of a nice plaque or something to that effect. And we will be mailing those out to the students just because of these particular conditions in these times. So just wrapping up, I would like to throw it out there for those of you students who were listening. There may be projects that you may be thinking of, mentors, there may be students that you have that are doing really great things. And so I just invite everyone to our next Research Symposium. And there are a lot of really great things going on campus. And just because of this kind of coronavirus business, we weren't able to have all of our presenters present. But we are very appreciative of those that did, and we very much thank you for your time. I think that this was a great success, and I was very, very excited and feel very fulfilled to see the work that our students have done and the work that our mentors have put forward in helping them with it, as well as the really great work of the Applied Research Committee. So I thank you all, and I wish you a great day. Thank you so much for attending our conference, everyone. And with that, we'll end the meeting. We will have a recorded copy of this at some point, and I'll send out information on where this can be accessed. Have a great day.